Okay, today we're talking about comparison-based sorting algorithms. Let's start off by defining some terms. First is stable. We say a sorting algorithm is stable if it doesn't change the relative ordering of equivalent entries. So as an example, say we have the sequence 2, 1, 1. We have two 1s in our sequence, so I've denoted them by 1a and 1b. A stable sorting algorithm will put the a before the b in the final sort because a came before b in the original sequence. Now, if it's not stable, it might flip the a and b. So the result might be 1b coming before 1a. Now, this is still properly sorted because 1s come before 2, but equal elements have been rearranged. Internal sorting means we keep all data in primary memory. External means we are able to split the data into different memories and sort them in subsections, which can come in handy when we want to sort a huge array and only part of the array could be stored in RAM at a given time. And then what does comparison-based sorting even mean? We're talking about comparison-based sorts today. Well, it means that we're sorting by comparing the elements in the array with other elements in the array. So the only information we need is from the compare to method of the elements, or if they're primitives, the less than, greater than signs. And then inversions are just a pair of elements out of order in your sequence. So as an example, if I have the sequence 4, 1, and 2, that has two inversions because 4 and 1 are out of order, and 4 and 2 are out of order. Okay, so we're going to be talking about 7 sorts today. They're all listed there. But before I would jump into that, last thing, I want to mention this fact that all comparison sorts are lower bounded by n log n runtime in the worst case. Now this is a pretty interesting fact because it means that any sorting algorithms that are based on comparing values are going to be in the worst case at least n log n runtime. So this applies to any future discovered sorting algorithms, any ones in the past. So let's talk about why this is the case. Now, don't worry if you don't completely understand this proof. It's not critical for this course, but I'll outline it. So comparison-based sort is one in which all decisions are based on comparing values. So you can think about, okay, you're using an if statement to see if one element is less than or greater than another one. So imagine your algorithm as a series of actions based off the results of a sequence of true-false questions. So basically your algorithm is just a sequence of true-false questions. Now a correct sorting algorithm must generate a different sequence of these true-false answers for each different permutation of your array because we need different sequences of actions to sort each different permutation. So there are n permutations in an array of size n. Okay, and then if we ask d true-false questions, each question can have like 2 different answers, true or false, so that generates 2 to the power of g different true-false sequences. So, as we said in this second blurb here, the number of true-false sequences, we want that to be greater than or equal to the number of permutations in our of our array, so that each permutation has a different true-false sequence. Because the true-false sequence corresponds to a different set of actions that we need in order that will be sorting the array. So if we fill that in, the number of true-false sequences, that would be 2 to the power of d, as we said here, and then the number of permutations, if our array has length n, is n factorial. Then if you take log to both sides, we get d is greater than or equal to log of n factorial. Log of n factorial is in theta of n log n, and I've linked a proof here in the slides, which I won't go into right now. But then that means d is greater than or equal to n log n. So the algorithm spends, like our sorting algorithm, will spend a lower bounded amount of time, like by d, asking d questions. So in the end, it's going to be at least n log n time. So that's the outline of the proof. Okay, let's now jump into actually going over a review of the actual sorting algorithms. First up is insertion sort, the classic. So it's pretty straightforward. The first step is just looping over all of our elements in our array. And then for each item you find, you insert it into its correct place among all items you've looked at so far. So let me go over a little bit of a demo to make it more clear. Essentially, this is our array, and we start off with like a sorted portion of the array and an unsorted portion of the array. When we first start off, everything is unsorted to the right, and we're looping over the items and then inserting it into the correct place among the sorted collection. So we're going to loop and insert B into the sorted collection. Awesome. Now we're going to look at E, and it's already in the right place now, just at the end of the sorted collection. And then we're going to look at C, and we're going to insert it in the right place among B and E. So that's going to move here and then here. And now we're looking at A. So trying to put it in the right place in the sorted collection, we'll move it like 3 hops to the left. So it's going to move here, 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 here. Now it's sorted. And then last we have D. It's going to sort here. And now we're done. There's nothing left in the unsorted side of the array. This is the code for insertion sort. So you can see this outer for loop. We're just going through all the elements in the array. And for each element we look at in the array, you go to the previous element and try to put it in the right place. So that's what this second for loop is doing. So you can see it's starting at I, and then it's decrementing. So you're trying to move like I, that element you're looking at, to the correct place in the previous elements. And you determine whether or not to do that to see it by whether the array at position j is less than the array at position j minus 1. And if so, then you swap those elements. So depending on how your array is structured, you might go through this for loop a lot, or you might not go through it a lot at all. So this outer for loop denotes we're definitely going to have a linear runtime at least, and then based off how many inversions we have, that's going to affect whether it's like much worse than linear or not. In the worst case, say we have an array in reversed order, so like descending order, then every new element we consider will have to go to the very front of the array. So we're going to have to do like one swap, then 2 swaps, and 3 swaps, ... to the very last element. That's going to move like n swaps. So that's going to be n squared in the worst case. Best case is no swap, so we never enter this for loop, so we just go through one time. Okay, so that's just what I talked about. Best case n, worst case n squared. So you can also write the runtime in terms of the number of inversions, which I'll get back to later. And then it's stable. So as long as you never swap elements that are equal, the relative order of equal elements are preserved, so this is a stable sort. Okay, let's talk a bit about inversions. So inversion is a pair of elements out of order, and I'm going to argue that for every inversion, insertion sort needs to make 1 swap. Not going to prove it, but I'll show it through an example. So say we have the array 1, 3, 4, 2. There are 2 inversions, 3 and 2 are out of order, and 4 and 2 are out of order. And what insertion sort will do is going to swap the 2 backwards twice for it to be in place. So it's going to like put it there. So it's going to have to make 2 swaps, and there were 2 inversions. So in general, the runtime of insertion sort is the number of inversions, k, plus n. Always plus n, because remember we always have this outer for loop, which is going to give us a linear runtime. So if k is small, linear, so if k is n, or even n log n, insertion sort runs quickly and can potentially be faster than merge sort and quick sort. So something to keep in mind. Okay, moving on to shell sort. Honestly, it's discussed in lecture. We don't go into it that much in this class, but basically it's an improvement on insertion sort by first sorting distant elements. And how do you determine what distant elements are? Well, you'll compare elements that are a specific gap apart, and then you'll progressively make the gap smaller until you eventually have a gap of 1. So say you can choose gaps that are orders of 2, so like 16, 8, 4, 2, 1. And what you do is, given an array, you look at all values that are 16 elements apart. So like every pair of elements, 16 elements apart, you're going to compare that pair and see if they need to be swapped, like see if that's an inversion. If so, swap them. And then look at like another pair of elements, 16 elements apart, etc. And then after you've done that, you'll look at all elements 8 apart. And then all 4 apart, all 2 apart, etc. And under some cases, this can be faster because it sorts some out-of-order elements that are far apart faster than insertion sort would do so. There is a proof in the notes as to why if you choose orders of growth that are gaps that are powers of 2, you can get n to the 3 halves runtime, but you don't actually have to know why that's the case. And this is not stable because swapping a gap can definitely reorder equal elements. Okay, now we're going to talk about tree sort, and in order to understand tree sort, this is a reminder that an in-order traversal of a binary search tree will always visit nodes in sorted order. So basically, if you have a binary search tree, and then we do an in-order traversal, that's going to give us all the sorted values. So remember to take a traversal of a tree. You can imagine like you're wrapping a string around the tree. And then for in-order traversal, whenever that string hits the bottom of one of the nodes, that means you've visited that node. So if I follow this string, the first node I'm going to visit would be 1, because I hit the bottom here. Then it's 3. And then I skip 6 for now, because I'm only hitting the left side. Then I go to 4, then 6, then 7, 8, 10, 13, 14. So as you saw, I went through those nodes in sorted order. Okay, so tree sort is basically just adding all your values to a binary search tree and then take the in-order traversal. Super simple, super nice. Love this sort. The one caveat is we want to assume that your binary search tree is self-balancing, which means it maintains like a bushy rather than spindly structure. So if you have a bushy structure like this, the number of levels in your tree is roughly log n, because our branching factor is a power of 2. Our branching factor is 2, so we're at every step we get 2 more children, so we're going to have log base 2n levels. So if we add n values, that's going to be n times log n time, because doing a traversal is linear. The caveat is if you have a spindly tree like this is already also a binary search tree technically, but then we're going to have potentially linear time in adding a value. So then it could be n squared in the worst case. But if you use a self-balancing BST that ensures a bushy structure, then it's going to be n log n. And this is stable as long as you make sure that when you're adding a value, you don't like rearrange equal values. Okay, moving on to selection sort, we're just powering through these. Here's a pseudocode. For every element in the collection, your array, you find the smallest remaining element in the unsorted collection, and you add that to the end of the sorted collection. So when you first start, the unsorted collection will be the entire array you're dealing with, and then over time you're going to grow your sorted collection. Okay, so here's an example. So this is the array we are starting out with, and I've marked in red the smallest remaining element in the unsorted collection. So that's going to be 11 because everything's unsorted to start with. And what we're going to do is we're going to add that to the end of the sorted collection, which is just like the very beginning of the list because our sorted collection is empty. So we're going to swap 64 and 11. Okay, like that. And then the next step is finding, okay, now the next smallest remaining element, which would be 12. Okay, so we moved now 12 here, and we swapped it with the 25. The next smallest is 22, move that here, then it's 25, and then it's 64. So then we get a sorted array at the end. And here is the pseudocode. Okay, so the pseudocode is basically, this is the actual code, which is essentially the same idea as the pseudocode. I'm going through all the values, and I'm finding the smallest element among so k starts from 0 and it goes to the length of the array n. So when k is 0, I'm first starting off, so I'm trying to find the smallest value in the entire array. And then I put that at the very front. And then when k is 1, I start searching for the smallest element starting at the first index. So like here, when at this was step 0, I search for the smallest element in the whole array. Step 1, I search for the smallest element starting at index 1, and then index 2, then index 3, etc. So this for loop here means like when k is 0, we're going to be searching n elements. Then when k is 1, we search n minus 1 elements. When k is 2, we search n minus 2 elements, etc. You get the idea. Eventually, we have this sequence like 1 plus 2 plus 3 plus ... plus n, which we've seen time and time again. That's n squared. So the runtime for selection sort is n squared, and this is always the case. Even if your array is already sorted, selection sort doesn't know this. It's going to keep searching for the smallest element. So it's n squared in the best and worst case. Okay, moving on to heap sort. Sort of a similar idea to tree sort in a way. Like you can imagine throwing your stuff in a data structure that can help you sort it. So what we're doing with heap sort is throwing all our values into a max heap, and then you repeatedly pop off the largest element from the max heap and add that to the end of your array. So the difference between this and like tree sort is with a tree sort, you need a separate data structure, like for your binary search tree. Whereas with a heap sort, if you recall, we implemented heaps using an array. So you can actually just convert your array that you're trying to sort into a heap, and then you can sort it entirely in place. So what we're going to be, that's why we use a max heap instead of a min, because by converting to a max heap, then when you remove an element from the heap, you can just put it at the very back. That's going to like create an empty slot at the end of the array because you removed an element, but you're just going to go ahead and put that element that you removed in the empty slot because that's the max element. So it should go to the end, if that makes sense. I have an example here. So say this was the original array. So first step is to convert it to a heap, an array-based heap. And you can actually do this in linear time. It's called heapify. And the way you do it is you just call like sync or bubble down on every single element in your heap. And there's a proof on why that's linear. You don't really need to worry about it. But okay, so we have our heap, and then you remove the max element. So once the max element is 8, so we're going to remove that, and then you'll have to like reshuffle the array to make sure it's still a heap. So that's going to give us this following heap. And that, notice that gave us an empty slot. Well, that's perfect because that's the last element in the array where the max element should even go when it's sorted. So then we're going to just add that element we removed to the last slot in the array. Okay, so in essentially all cases, this is an n log n runtime algorithm because our heap operations are going to take log n time so every time you remove the maximum element from a heap, that's log n work because you need to replace that max element with the minimum element and then bubble it down. And we're going to do that n times because removing elements n times, so it's n log n. The best case where it's linear time is if all the elements are duplicates. So then like your bubbling down is just constant work. But for most intents and purposes, it's an n log n runtime. It's difficult to make this stable as well because the heap operations can reorder equal elements. So it's not stable. Okay, now we're moving on to another class of sorting algorithms, still within comparison-based sorting, but the approach is called divide and conquer. Divide because we're splitting our collection into parts, and then we recurse on those parts. And then conquer the parts. Conquer means we do something with the parts to make them sorted. Okay, so merge sort, my favorite sorting algorithm, is relatively straightforward and like elegant in its approach. You just divide the array cleanly into two halves. If it's odd, then one half will have one more element than another, which is fine. And then you call merge sort on each half, so it's recursive. And then you're gonna taking that recursive leap of faith. I'm assuming merge sort returned two sorted halves. Then you merge together the two sorted halves. And merging two lists that are already sorted takes linear time proportional to the lengths of the two lists. So what's our base case for this recursive algorithm? Well, if your array input has length 0 or length 1, then it's already sorted, right? So that's basically it. And what ends up happening is, do I have this? Yes. Okay, so you're going to repeatedly make recursive calls like on the two halves that you split. And since you're creating two children and dividing the work in each children by half every step, that's going to be log n levels. So at this point, we just have log n work because we're just splitting in half and making recursive calls. Then we hit the base case here where all the subarrays are of length 1. So from this point onward, when we return from the recursive calls, we need to be merging those arrays together. And as I said in the previous slide, merging lists takes time proportional to the number of elements in the list you're merging. So at every level, merging at that level is going to take a linear time because you're merging like n pairs of elements. Or like here you're merging 1, 2, 3, 4 lists together into okay, here for example, this merge is going to take n over 4 time, and you're going to do that 4 times. So long story short, it's just the merging takes linear time per level. We have log n levels, so it's n log n work. Yeah, so runtime is always n log n, best case, worst case. And this is an external sort. So this is something I talked about at the very beginning. What this means is if you have like a super huge list and we can't fit all that data in RAM, think about it like when we talk about RAM, we say you have 4 gigabytes of RAM, 8 gigabytes of RAM. What if your list is more than 8 gigabytes? Like you're sorting huge amounts of data or something. Well, you can split the arrays because you're splitting them in half, and then you call merge sort on those subarrays so that like a certain subarray can be small enough such that you can bring it into RAM and sort it. So that's useful. This is stable, and because it's stable, Java uses an optimized version of merge sort to sort reference types. So this is like objects, and this is useful because you could have two objects that are like equal based off the dot equals method, but they're different objects, and a developer might actually care that the relative order is preserved, so by default, Java uses a stable sort. Okay, let's move on to the second divide and conquer algorithm, which is quicksort. With quicksort, instead of dividing the array perfectly in half, we're going to choose a pivot. So in this graph tree here, we choose like the last element of like each subarray to be the pivot. So for example, here the pivot's 3, and then we partition the array around the pivot. So you move all elements less than or equal to the pivot to the left of the pivot, and then move all elements greater than the pivot to the right. So you create two subarrays, and their lengths are determined by how many elements were less than or greater than that pivot. So here, partitioning around 3, we get like 4 elements on the left, 4 elements on the right. It's pretty nice. And then you run quicksort on each subarray. So now for this new subarray, the pivot would be 1, you split it accordingly. Now the pivot would be 6, you split that, etc. Okay, so what's the runtime? Let's analyze this a bit. So you partition the arrays and recurse on each piece, and then when you return from the recursive calls, there's no merging to be done because you've already done the sorting by arranging the elements around pivots. So you just have to concatenate your results together. So that's this, I've outlined it in red. We just concatenate these base case values together and return them, then that's going to be a sorted array. So this differs from merge sort, where we had to go down to the base case, and then when we returned, we had to merge. Now when we return, we're good to go. So there are log n levels in general. Assuming you've split the arrays into roughly equal halves, then we're going to have log n levels similar to merge sort. And how much work are we doing per level? Well, partitioning an array takes time linear to the length of the array, right? Because you have to look at every single element to see if it's less than or greater than the pivot. So that's going to be n work per level, log n levels, n log n. So that's n log n is the average case and the best case. There is a worst case, though, for quicksort that's actually worse than n log n. And that worst case is n squared. So when does this occur? This occurs if your pivot does a really bad job of splitting your elements into halves. So this has to be pretty extreme because you don't need to have perfect halves. Because if it's log base 2 n or log base 1.5 n, that doesn't matter asymptotically. But if it does a really bad job of splitting your array into halves, for example, if you have a sorted array and you choose the first element as the pivot, then you're going to get something like this, where, okay, I chose 1 as the pivot, so I look through my whole array to see if any elements are less than 1, and then no, so then this is now my entire right array, and then my new pivot is 2. I have to look through all the elements to see for any elements less than 2, etc., etc. So basically I'm going to be doing n work, n minus 1 work, n minus 2 work, etc., until I do 1 work, and that's the 1 plus 2 plus 3 ... plus n sequence was seen before, which is n squared work. Yeah, so one thing to mention is this specific example is, if you have a sorted array and then you chose this first element as a pivot, a reasonably good sort of strategy for trying to get around worst case scenarios for quicksort is just randomize your array when you start off. Okay, so review of quicksort, the runtime depends on the pivot. In the best and most typical case, it's n log n. For packages where you will actually run quicksort, they'll ensure that they do something to the array or that they have some pivot selection strategy to avoid the worst case. And stability depends on the partition strategy. Typically, quicksort is not stable, but Java does use it for sorting arrays of primitive types. So if you do arrays.sort on a primitive, it will use quicksort because it doesn't matter if it's stable for a primitive type. You can't tell whether numbers are rearrange their order of equal values because a 2 is the same as any other 2. It doesn't make a difference. Okay, so last thing, I'll quickly mention radix sorts. They're not covered on this week's exam prep, so I'm not going to go in depth, but basically radix sorts are sorting that's not comparison based. So this means it can be very fast and faster than n log n, but it only works the ones we're talking about only works for keys that can be alphabetized. So basically values that you know beforehand the order of. So you have a finite number of values that you're going to be sorting and you already know their order ahead of time. So typical example is if you're sorting digits which have values between 0 and 9, and you already know their order, 0 comes first, then 1, etc., a radix sort is perfect for that. So the base of a radix sort is distribution counting, which takes linear time. High level, imagine you have you're sorting 1,000,000 numbers, but each one of those numbers is a digit between 0 and 9. You could use a regular sort that we talked about, like merge sort or whatever, that would take n log n, where n is 1,000,000. So that'd be very slow. Intuitively, you should think we can do something faster if you know all the elements between 0 and 9. You can just loop through your array, and whenever you find a 0, you know, okay, that should come first. So, you know, you could put that in like the 0 bucket. You can keep track of how many zeros you've seen, then you can keep track of how many 1s you've seen, how many 2s, etc. And then you can just populate a new array of length 1,000,000 and just fill like the beginning of the array, fill it with zeros based off the number of zeros that you counted, and then fill the next part of the array with 1s based off the number of 1s you counted, etc., right? So that would end up taking linear time rather than n log n time. So radix sorts are an extension of this, or an application of distribution counting, where you sort large numbers, so numbers that aren't just 0 through 9, but you sort them by their digits. So for LSD, you sort based off the least significant digit first. So you sort all the numbers based off like the 0th digit, then based off the 10th digit, then the 100th, etc. And as long as your sorts are stable, the numbers will be like properly sorted by the end. And MSD, most significant digit, does the same thing, but starting from the most significant digit and then working its way down. So then sorting all the digits takes a linear time, and if k is the length of the maximum number in your list, then you're going to have to process like k sets of digits, so that's going to be k times n time for this radix sort. Yeah, that's a high-level overview, but we're going to be going over comparison sorting examples in the worksheet. Okay, so this is a cheat sheet for all the comparison-based sorts that I made back in the day.